Hello and welcome to DVCon Europe and to this tutorial where we're going to give you an update on what's been happening with UVM-AMS and Accellera. My name is Tom Fitzpatrick of Siemens EDA, and I'll be introducing today's session. Later I'll be joined by Tim Pylant of Cadence, who will go into more detail about how we plan to accomplish our goals of bringing AMS functionality to a UVM environment. Before we can discuss the proposed approach in any detail, we must agree on the terms we'll use to have that discussion, just to make sure that we all understand each other. And if you're like me, you'll have a hard enough time understanding the analog stuff, so it's best to start from a known good place. When we refer to analog mixed signal or AMS simulation and verification, we're referring to one of two things. The first is a system where we combine the co-simulation of the digital side, including real values, in a digital simulator with the analog solvers to handle the electrical stuff on the analog side. This is sometimes referred to as analog mixed signal co-simulation. The other is where we use an event-driven simulator, which many of us are used to solve both the digital logic and also the analog behaviors using real number models. This is referred to as digital mixed signal simulation. Since we're talking about using the universal verification methodology to verify analog behaviors, we should also agree on what we mean by UVM. The UVM is a class-based methodology in System Verilog that helps you create robust, reusable, interoperable, and modular verification IP and other test bench components for digital verification. The UVM has been around for 10 years, and there are plenty of resources available if you want to go and learn more about it. We're going to assume a working knowledge of UVM basics for this tutorial. As you'll learn in today's presentation, UVM-AMS is intended to take all of the UVM advantages from digital verification to provide a unified, comprehensive verification methodology for analog or mixed signal systems using either AMS or DMS simulations. In a classical UVM test bench, communication to the DUT is managed through a component called a UVM agent, sometimes called a Universal Verification Component, or UVC. There's typically one agent for each unique interface to the DUT, and an agent is composed of several kinds of low-level UVM components. Since UVM test benches are class-based, they communicate with the DUT through a virtual interface, which in System Verilog serves as a pointer to an instantiated interface that defines the pin-level connections to the DUT. In the UVM agent, the driver is responsible for wiggling the pins in the virtual interface, either directly or through a task call in the interface. The sequencer is responsible for running one or more sequences in the agent that define the communication in terms of transactions, which are implemented as UVM sequence items, each of which contains fields for various aspects of the protocol, such as address, data, possibly wait states, and other information. The driver takes the sequence item and uses the information defined in it to wiggle the virtual interface signals according to the protocol and the sequence item contents. On the response side, the monitor sees the pin-level behavior in the interface and recognizes bus operations as transactions, which it then can write out to coverage collectors, scoreboards, or wherever you need it to. Each agent is also configurable using the UVM config database to define specific information for the agent itself, such as should it be active or passive, but also for the driver and monitor if necessary. Perhaps the major difference between digital and analog simulations is that digital signals tend to be discrete, where analog signals may be continuously changing. Many useful analog signals can be composed of other periodic waveforms, like a series of sine waves. Taken to the extreme, we also know that a square wave, which is modeled digitally as set to 1, wait a bit, set to 0, and wait a bit, and so on, could actually be modeled as an infinite series of harmonic sine waves, although we would never actually implement it as such. In actuality, a sine wave can really be controlled simply by 4 control values to define the frequency, phase, amplitude, and DC bias of the generated signals. Once we understand this, we can define a UVM transaction that encodes the properties of the desired sine wave as real values in the UVM sequence item that can then be passed to the UVM driver, which will use those values to generate the signal. So the UVM sequence item will contain fields for all desired control parameters of the analog signal we want to generate, and the driver will use those settings to control the signal generator. In this way, we continue the UVM paradigm of having a relatively simple interface for the test writer and giving us a way to control the generated signal as we need to. One of the first things we did in the UVM-AMS working group was to make sure that we all agreed on the requirements of what we're trying to accomplish. Our main goal was to be able to build on existing UVM infrastructure as much as possible. With this in mind, we felt that the best solution was to define analog behaviors as a set of parameters that could be encoded in a UVM sequence item that could then be used to generate the desired analog signals using an analog resource that we're calling an MS bridge. Tim will show you how this is going to work in a few slides. We also want to be able to measure the properties of an analog signal and rely on a UVM monitor to turn those properties back into a sequence item for use elsewhere in the system. And we also want to be able to configure things either using the UVM config database or using specialized sequence items that the driver can use to integrate into multi-channel test sequences. Of course, we'll be able to take advantage of constraints in UVM to set or limit control values based on specific configurations or test needs. And finally, we want to be able to monitor the analog signals and identify the properties of a given signal so that we can use the UVM monitor to collect coverage on the corresponding sequence items. By making all of this an extension to UVM, we expect that users will be able to build on their existing UVM infrastructure as much as possible when they need to incorporate AMS designs into their system. For example, if you change your DUT to go from a real number input to an analog input, you should be able to reuse your existing UVM environment and simply extend the definition of the UVM agent to include the new functionality for that pin. Similarly, you'd be able to use the factory or the config database to cause a different sequence to be executed, which might now include the control transactions for the analog behavior. The rest of your UVM environment wouldn't have to change, which is one of the key advantages of UVM in the first place. So we're simply taking that philosophy and applying it to the analog mixed signal verification. Just to see what I mean about combining multiple signal generators to create more complex input signals, here's a quick example. We might have a signal source that we define to be a sine wave. Again, this would be defined by a UVM sequence item to specify the amplitude, frequency, phase, and DC bias. We may also want to inject some noise onto that signal. As we'll see, we have some flexibility in how we implement this. The noise source may be a different sequence item, and it may be generated as part of the main UVM sequence, which we might use to inject noise at predictable intervals within the sequence. Or it may be generated by a different sequence, in which case the noise might be injected randomly. In either case, the driver will detect the sequence items as either signal or noise and pass the appropriate information on to the signal generator or generators, depending on the setup. Now I'll hand it off to my colleague from the UVM-AMS working group, Tim Pylant from Cadence, who will show us in a bit more detail how we're planning to make this all work. Tim?
Seems to be an issue with the video. Please hold on one moment.
Hey, Tim, are you available to do your part live? I'm not sure what happened to the video.
Yeah, yes, I'll have to pull the slides up. Hold on.
Apologize for that, Odom. I'm not sure what happened.
Yeah, I'm sorry. The video that was provided to me is only 10 minutes long.
That's not the right one. Something happened. Sorry about that.
I just coming up. Hold on. Right. Let me share my presentation. Hey, Tom, video good?
Yeah, it looks good to me.
All right.
Good.
Okay, thanks, Tom. So we're going to take that UVM environment that Tom was talking about with your standard UVC driving a DUT, and we're going to show how the bridge works in that environment. So as he talked about, we're going to insert this MS bridge, and this is required in order to get that continuously changing signal that Tom mentioned. So we can't just, because UVM is driving a single value, you need to be able to convert that into a continuously changing analog signal, as well as being able to interface with electrical as well as discrete real numbers. So we add in this MS bridge. We carry the interface over, so you still have to have that interface. And then we put in the analog resource module, and this is what generates the signals to drive the DUT. And we also add in this additional component that we call a proxy or an API. And this is what programs the analog resource. So just imagine that you want to create a sine wave or a sawtooth signal or something like that. So you couldn't do that through the interface signals because you would just provide a single value. So with the proxy, and I'll go into more details about this, with the proxy, you can program the analog resource to generate that signal based on the sequence that's going on in your UVC. So the proxy and the analog resource in combination with the interface all go to make up the bridge, and that drives the signals in the DUT. So the interface is still there. It's still used to convey the information across your digital or discrete value signals. So you still have control signals and things that you can drive directly from the UVC, and those will communicate through the interface. And this is a complete MS bridge. If all you're doing is driving real numbers, then maybe you don't need a proxy. Or maybe you're only driving continuously changing signals that have to be programmed through the proxy, then you wouldn't need the interface. So the proxy and the interface can be used in conjunction with each other or individually, depending on your needs. And then again, that analog resource is typically going to be Verilog AMS if you need to generate an analog type waveform driving into an electrical or something, or it could be system Verilog or Verilog. There's no restriction on the analog resource, whereas the MS bridge itself is a system Verilog because it does need to work with the class-based proxy. So I'll talk about that in this next slide. So if you require the behavior in the presence of an analog component, such as capacitors, resistors, voltage sources, etc., then you would need to write a Verilog AMS block. And you can do that for that analog resource, and you can insert it into the MS bridge. And then you can control that, like I said before, from the proxy and program up the behavior for that. And then that API is used to program behavior. So you can say what the voltage and current are, maybe the frequency, and how is it sampled, any kind of behavior you want, you can program through this proxy. And then the analog resource would then generate the signal or signals that would correspond to the DUT. And all the signals go through the analog resource. And so if you're, even the discrete signals would go through the analog resource and connect up to the DUT. So the analog resource is kind of a one-to-one mapping of signals between the MS bridge and the DUT. So here's an example of a proxy. And so there'd be proxy class, and you can define all your API that you want to use within the proxy. So in this case, we have a set capacitance function and a get capacitance to write and read the capacitance for the bridge or for that analog resource. And so in the bridge, you would extend that proxy, fill out what exactly a set capacitance does, what the and how that responds. You would also, let me get a pointer here. You would instantiate the actual core. This is your analog resource. And then you would connect up the, or you would construct the proxy within the CAP bridge. So the CAP bridge is, and this is our MS bridge. Again, we have our resource, our proxy, and then we construct the proxy. And then in our test bench, we instantiate the bridge because it needs to be within a module in order to have that continuous behavior. And then you can use a config to pass the proxy, and then you start up your test just like normal in UVC for a UVC. So inside of our MS bridge, we have our proxy class. There's another example. We have our set ramp. So we're going to pass in a value, 2 values into our set ramp that are going to set the values for TF and TR, rise and fall within our analog resource. So those are both real numbers. And then we have our target. I'm sorry, our rise and fall will be TX, and then our target will be val. And then we also have a function, get value. So this is a push, and then of course, those get pushed over into the analog resource. And then once those values will then get set within our analog block here. So this is obviously a UVM-AMS analog resource. So it will be used to generate voltage or potential on the plus and minus signals. And then we have our pull function that just goes off to the core typo there and calls the get voltage function that gets the voltage as a real value. So it reads it, pulls the voltage off the plus minus, assigns it into get voltage, and returns that value back to the API. And then finally, there's a monitored value in this class. So we have a continuously monitored value here for V plus minus, that every time there's a abs delta change between plus and minus, that this value will be updated, and that will go over and be assigned back to the iProxy plus minus, which is inside the proxy class. And so now the UVC can communicate through that proxy class to monitor that value as well. So these are examples. You can have all of these type of functions, push functions, pull functions, monitored values, or any combination of them. So on the push-pull, how does the synchronization work? And so here's some, so in this case, we have some AMS code. So this discrete value is being passed in there, and this analog value is being triggered. So you can see different trigger points for when the discrete value came in. It starts the value, and then when the rise starts, there's a transition, and then when it completes, there's a transition. And so different points along here are going to be passed back from the analog back to the UVC. And so you can use function calls from UVM to monitor the values and see when the actual discrete value that you passed in has transitioned through all the analog steps, because there is some delay, of course, since analog has more of a real-time function to it. So you need to wait. When you go high, you have to wait for that high to actually transition in the analog, and same thing when it goes low, you want to see it transition. And you don't want to use a pound delay because it's not locked in necessarily with the analog simulation. So you need to have this triggering type mechanism to do the handshaking. And so let's look at how that would work. So we have our proxy set capacitance, and we're going to pass in the rise fall and the capacitance value. And then we're going to call the wait for cap EOT, the end of transition. And so that will then connect up with the set capacitance inside of our bridge. And it will assign the capacitance values inside the core, inside of our analog resource. So inside of our analog resource, we assign the values down in there. And so inside the analog block, we'll respond when we set those values. And so we have this transition occurring by taking the values of the rise fall. We have the transition going back to cap tran, and that will be read back over here in our set capacitance. So it's going to wait for the cap tran value to respond to the values that we set in the first statement. And then that will then trigger up here in our proxy. So we say, okay, we've hit the end of transition. So we see that the value has gone through the analog transition. And so now our wait can finish and we can continue on. So this is just a very safe way to do mixed signal type of driving when you have to wait for the analog solver to respond back to the putting a digital signal out there. So this is some of the handshaking that you can do from UVCs through the proxy and into the analog resource. Oh, and then once that's finished, then you have your clock. And then again, you have a this EOT again will be monitored here, and that will trigger as well. So let's look at our doubler example. So in this case, our DUT is going to take in an input, a clock, and an output, and then monitor the output. And so the analog resource in this case is just and we're going to use just a real number model for our analog resource. So we're not doing any kind of true analog modeling that involves the analog solver. We're just using real numbers. So in that case, all we have is an interface that is going to drive the signals that control the in and clock, and will monitor the output. So that's very simple. Here's just the example of what that would look like with using real number modeling. You're just doing assign statements and passing values into the different signals and monitoring the output. Okay, now you come in here and everything stays the same. The UVC is the same. We're using the same sequences. The interface is the same, except now we're going to replace the analog resource with a VAMS model. So instead of using a real number model for the analog resource, we'll use a VAMS model. And in this case, you need to create connect modules or some sort of translation from the real numbers that come in through the interface, because remember, we're driving real numbers in this case for our in and clock. And so you need a connect module that will convert the real number coming in to an electrical value that can drive the VAMS or SPICE model. The clock is a digital clock, so you don't need a conversion element there. And then the out will be an electrical signal coming out, and so you need to have a connect module that will convert the voltage coming out into the corresponding real number that will be passed back through the interface. But everything else stays the same. All the connections stay the same. The interface stays the same. The UVCs stay the same. All you do is swap in the analog resource. And again, for that, you see here, we're using an analog modeling instead of the real number modeling for that. And then here, we're going to use a proxy. So we're going to add a proxy and now drive in a continuously changing signal or something. So in this case, we would need to change the bridge slightly and create the proxy that will be used in conjunction with the interface to program. So in this case, we're going from a logic to an electrical. So we need to program in maybe what the voltage or the VDD for the analog resource is. So it knows what a logic 1 should be on the electrical. So you would have a proxy here, set voltage or set VDD, that you could say 1.8 volts. And so if it sees a logic 1 comes in, it knows to drive an electrical value of 1.8 volts for a logic high. So that's how you would use the different variations of your analog resource between real numbers that are very straightforward, just interface values driving straight through to the DUT, a BAMS model that uses the same real numbers, but you have to put some sort of a conversion element in there to convert from the real number to the electrical, but that's a very direct method. And then finally using a analog resource that takes in logic values, in which case you have to program the analog resource to understand what a logic 1 is, where you program the VDD. So those are the 3 different types of analog resources that you could, and how you would have to modify your analog resource or the bridge to support the 3 different models. But the key is that the UVC stays exactly the same. You use the same sequences. In most cases, I guess with if you add a proxy, you would have to add a proxy on the UVC side. But in most aspects, everything stays the same, including the connections to your DUT. So the other thing that UVM provides a lot of value for is in the debug and error reporting using the UVM info and UVM warning and UVM errors. So we want to take advantage of that with UVM-AMS as well. There's just a slight modification that you need to do in order to handle, again, the differences with dealing with analog signals over discrete signals. So we have the UVM info, warning, error, and fatal that are all built in, that are all controlled with standard methodologies through the UVM report server. All this is standard UVM. And so we want to take advantage of that with the UVM-AMS. So of course, because that is system Verilog, you cannot put it into system Verilog AMS modules. So you need to be able to, you have to write the UVM info and other messaging in system Verilog. So how do you do that? There's a capability called upscoping, and I'm going to show an example of that. And so that's the solution that we're recommending. It's very simple. You just need to include a file in your Verilog AMS analog resource to define some parameters. You include it into your system Verilog bridge file that's going to wrap the UVM info messages. And then you just make reference to UVM info, the wrappers instead, within your digital and analog blocks. So let me show you an example of that. So in our BAMS model, so the analog resource, we're going to create a UVM path, and we're just going to set the value of the path equal to whatever our instance path is within that module. So this would point within our MS bridge. So this will be our TB, MS bridge, and in our example, core. So MS bridge core, our analog resource path. And then we'll create our message that we want to print out. And then we'll call UVM info. And this UVM info is that wrapper that we put around the tick UVM info from the UVM library. We'll pass it p-type, our message that we set, our verbosity, and then the UVM path. So this is kind of the unique thing that we're adding, is this UVM path down into the resource. So inside of our bridge, we have that package that we included that has this wrapper. So this is our UVM info wrapper that looks just like UVM info. We have our string ID, string message, verbosity level, and then the additional UVM path. We have to pass up the path because this is going to be invoked from within the bridge, not from within the resource. So we pass this additional path in there, and then we use the UVM, built-in UVM macro, UVM info context. And this works just like UVM info, except you can pass in the context of where that's working. And that's how we pass in the actual path of the resource. Instead of it reporting the bridge, it would report the resource. So very simple. It just adds this additional argument for UVM info, and now you can use UVM info down inside your analog resource in the VAMS model. And so when that gets executed, it's going to print out the same thing as normal. It's going to print out your time. And then this is the actual path down to iBridge, so that we see the actual path there, and then the message that we set up here. So some questions that have come up. So what's the value of UVM-AMS? So what we want to do is create an industry agreed analog mixed signal verification methodology based on UVM-AMS. Just like when UVM came out with the standard, IPs bloomed because there's now a standard way to work with your IP and provide a standard methodology for verifying it. And we want that same type of expansion of IPs and other offerings by standardizing on this UVM-AMS type of methodology. And it also becomes easier when moving between companies or hiring other people. If everybody is using the same methodology, then it's easy to come into a new scenario and be able to start writing code immediately. Another question, I currently use interface VIP, which supports only digital signals. So the objective here is to make AMS extensions to digital centric VIP. So as you can see from some of the examples, it works very similar. If you're staying in the digital or real number arena, things work very much the same. The analog resource just passes the signals through, and things work very seamless. If you want to take that and extend it and add some of the true analog natures to it, you just replace the analog resource, and it makes it fairly seamless to integrate digital VIP and extend it into the analog to the AMS VIP. So again, this last comment, it depends on the flexibility that you want to use, as well as what you want to extend. If you want to just keep using the digital signals, then of course that's easy to do. Your core or your resource just passes the signals through. If you want to extend it, you can do that as well. Is the working group going to develop specific VIP? And no, we're just developing a standard framework that people can build upon and utilize to build VIPs. We will have some examples out there to help show you how to get started, examples that like what we were showing in the previous slides that give you the basic understanding of how it works and the connectivity that you can take, you're free to take and extend on your own. So in conclusion, there is a need for a standard methodology for scalable metric-driven mixed signal verification. We're coming across mixed signal needs more and more frequently, and we need a standard methodology that takes advantage of UVM, but extends it to handle the mixed signal aspects of the verification needs. And we're hoping that the UVM-AMS standard that we are proposing, or that's being proposed here, will be able to address all the gaps that you have in your verification. It is a proposal right now, so it's still being tweaked to look at additional things that may not have been considered, but it's a good place to start from, and addresses a lot of the issues that come up in the mixed signal or AMS verification. And of course, it extends straight from UVM with the addition of that bridge to handle all those aspects. So we're trying to target true mixed signal, so analog mixed signal, where it can be a real number model, it can be a SPICE model, VAMS model, whatever. The same methodology handles all those aspects while still being able to leverage the power of UVCs with the monitor driver sequencer type methodology, along with being able to program those and take advantage of all the extensibility of the UVM class-based library, and of course the messaging system. So at this point, we have plenty of time available for questions and answers. So invite Tom back to open it up for questions. Tom, was there anything you wanted to add while we're waiting?
Tom, we cannot hear you.
Okay, how about now?
Yes, there you are.
Thank you.
Having microphone issues. Sorry about that. So thank you, Tim. We also have Johan Wechtendorf of NXP. He's a member of the UVM-AMS committee, so he'll be here. For Q&A, you can either enter a question in the chat and we'll get to it, or if you want to raise your hand, Autumn will unmute you if you want to ask your question live. So first question that I see from Graham: when will the demo code be made available? So the way we're going to do it, we're going to be having code in a GitHub repository that we'll use for examples that will be included in the standard. This is kind of a typical thing that we do with Accellera. So that code will be made available either on GitHub or some other platform when the standard goes live. So the standard, as usual, will be a document that will explain the methodology, probably define any APIs that we're going to include, similar to what's in the UVM documentation now. And then we'll also have a set of examples that will be in the document itself, as well as available to be run, probably through GitHub or something else. Next question, what is the timeline for this proposal to be available for use as an official release? At this point, we're probably looking at the earliest middle of next year. We don't have a set schedule. For the first version of a standard like this, we like to make sure that we have the right content and then worry about the date. We don't want to be date driven. So we're going to make sure that we have everything addressed before we ship it out. So we're hoping to get it certainly no later than the end of next year, but you know, I'll have to see how it goes. So
there was a question before that. Martin was asking about the functions that are in the proxy. Are those going to be standardized? So that's a good question. At the present, they're not standardized, but I can imagine certain functions becoming that you see used over and over, such as set voltage, set current, things like that, being so widely used that they by default kind of become standardized.
Yeah, I think there will be a certain set of things that will be standardized, but a lot of this is going to be application specific, so we're not going to be able to standardize on everything, obviously. But that certainly the goal would be to standardize on as much as possible. Next question: do you plan to create a one-size-fits-all UVM-AMS agent plus MS bridge, or would you split it based on specific analog MS interfaces? So I think it's, as Tim outlined, the MS bridge itself, and really the analog agent in the MS bridge is going to be very application specific, depending on whether it's SPICE or real number or whatever. So we expect that there will be a one-size-fits-all view of on the UVM side. So once you extend your UVC to include the proxy, that proxy API would be application specific. What happens inside of the proxy in terms of what gets called in the analog resource would depend on the abstraction layer of your actual DUT. So I don't think there's going to be a one size fits all of all of that. And since the MS Grid itself is a module, you will be able to extend it as you can a class. But the proxy itself should be reusable, right? You want to comment on that, Tim?
Yeah, so just like UVCs today, the methodology is standardized, and then people build standard types of UVCs on top of it, you know, USB or PCI or different types of UVCs, and those can connect up to anything that takes in that protocol. There might be, that's what we hope is going to happen with the UVM-AMS, is that the methodology is consistent. There's going to be a UVC and a bridge, and the bridge will have an analog resource and a proxy. And that methodology is consistent, and so people build standard analog type VIPs that utilize that methodology, and then any kind of DUT that requires a analog protocol that matches that can just hook right up to it and program it. You know, you can pass the bridge is system Verilog. It can be you can program it. You saw how we passed in used the UVM config to pass in where the proxy was. So you can use UVM config to control things in there, just like you would with a standard UVC. So long answer to say that, you know, not going to, the one size fits all hopefully is for the methodology, and then people will build off of that and start producing off the shelf.
Do you want to add anything to that?
Yeah, I would like to add something. So I also think that, let's say, the analog world is a lot more diverse than the digital world. So I think the variation, so something that cannot be a one-size-fits-all solution, will be this analog resource. So there's a lot of configuration involved, impedances, signal types, and so on. So that will always be an application-specific thing. And I think that this standard indeed proposes the blocks and the interfaces between those blocks, but yeah, how it is coded itself, that is up to a user for his specific problem.
Right, thanks. Next question, does the UVM-AMS working group also consider standard methods or elements for analog AMS or DSP signal analysis meters, such as SNR calculations, frequency meters, et cetera? So that's on the monitoring side, and that is something that we're looking at. You know, in digital UVM, it's a lot easier to write a monitor that will look at the signals on the bus and recognize when a transaction happens. On the analog side, it's a little bit more difficult. So Tim had a nice example of using the ABS delta thing to recognize when certain signals are transitioning in the analog realm and send that back. Again, some of these things similar to, you know, set voltage or whatever, some of these monitoring things will be able to be standard, but not all of them, right? So we'll do as much as we can. Tim, you guys want to comment on that?
No, that's exactly right. The monitoring is a little bit more fluid right now. We're and yeah, we're still fleshing out the monitoring side of things.
Okay. All right. So yeah, I mean, again, the big thing here is we wanted to start with UVM, right, which is now over 10 years old, has done a really nice job of defining a methodology for setting up modular reusable test bench components and relying on the extensibility of class-based environments in UVM, in System Verilog, to be able to reuse the same structures, but reconfigure them through the config database or extend things and bring in a new component through the factory without having to change the source code. So we're trying to reuse that philosophy as much as possible, right? And so when you get to the analog interface piece of it, that can't be class-based just because of the way things work in the simulator and the languages. So we wanted to get as much class-based stuff as we could to allow that interface to happen. And that's where the proxy comes in. So the proxy is there to define the API for dealing with the analog stuff. And again, you can have the same API with different implementations in the same kind of proxy, and then you can use the factory to define which proxy you're going to use in your UVM, your UVC or your agent. Right? So we extended the UVM philosophy as far as possible over to the AMS side. And we got kind of as far as we could, and then we said, okay, as long as we can do this much, the test bench is flexible enough to be able to respond when you change the abstraction level of your DUT. You're going to have to do a little bit of other stuff in the MS bridge and the analog resource to make that work, but the upstream part in the test bench works pretty much the same. So it's very similar to in a typical UVM environment. If you change the protocol of your DUT, you know, you can swap out one driver for another. The API that says I still want to, you know, write to this address or whatever from the sequence level is still going to stay the same. So we wanted to try to keep that philosophy as far as we could. And that's where we came up with the idea of the MS bridge and the proxy, the class-based proxy to do that. So I think we're pretty good. I'm, you know, as you guys all know, I'm much more of the UVM guy than the analog guy. So, you know, we have kind of a mix on the committee, and I think we have the right set of people to be able to identify the kinds of problems that we're facing in an AMS verification problem, and we have enough UVM expertise in the group to be able to make sure that everything's going to play as well as possible with the UVM. So that's really what we're trying to do. So, Tim and Yon, I'll let you guys make some closing comments. And
no, very good summary. Yeah, the ability to take advantage of all the UVM history that we have and working with the proxy, and as Tom said, you can use all the class-based features with the factory and overriding and UVM config and all that capability. and take advantage of all that, all the messaging. But now extended over into that bridge. And then the flexibility of being able to swap out the resource without having to change up. Again, trying to maintain that same type idea of UVCs where you don't change, you don't have to start over from scratch every time. You just configure and swap the resource. We're trying to maintain that type of modularity, reuse, and efficiency for your verification environment into the MS bridge and allow you to communicate with analog type signals.
Johan, you want to wrap it up here?
Yeah, so yeah, I'm considering if I will drop a bomb as well. So no, but I think it is really great to use the UVM methodology in the context of analog. We call it AMS, but also analog. I think the separation of test and the test bench and the DOT, that it is really great. So really offering reuse, so you don't have to write your tests every time again. There's one thing. And that is basically the bomb. That's then the question if we can bring UVM to the analog designers. I think that is a bit of a challenge. If they're interested, they're welcome, of course. But I think that it is really a great advantage to bring analog verification to verification engineers, mixed signal verification engineers, so that they will be able to verify their IPs and the systems and maybe even their ICs. In a real mixed signal context, regardless of the abstraction level of the DOT, and that's really the big advantage of this stuff. And that's great.
Great. All right. Well, thank you all for your attention. Really appreciate it. If you happen to work for a company that is an Accellera member, you're more than welcome to join the committee. So feel free to reach out to myself or Martin Barnasconi if you're interested. If you're not a member of Accellera and would like to be, you can also reach out to us. We'd be happy to have you. Standards only work as well as the people who volunteer to be on them can participate. So, we're all doing this. I wouldn't say necessarily in our spare time, but it's not necessarily the primary focus of our jobs. So the more, many hands make light work. So the more people that we can get on to help, and if you have something that you want to see in the standard, the best way to make that happen is to join the committee. So if this is the sort of thing that you're going to be using moving forward in your job, and you want to make sure that it does the kinds of things that you need it to do, the best way to do that is to join the committee and help us. So with that, I will again thank you for your attention. Enjoy the rest of the conference, and have a great day.